did her master's in Jadavpur University and then worked in our lab, nanoelectronics lab in TIFR, the JRF for around a couple of years, and then is right now doing some great work in ICFO Barcelona, and she'll give us some glimpses of her work there. And so we are eagerly waiting to hear from you, Ipsita, and you can start. Thanks.
Thanks a lot, Shubhajit, for this nice introduction. And thank you everyone for joining the talk today. I hope you can see my screen now, right?
Yes, we can.
Okay. So just a minute. Right. So today I'm going to give you a brief introduction of twisted bilayer graphene and some of my results, which are mostly magnetic field driven quantum phases in magic angle twisted bilayer graphene. So this should be the brief outline of my talk. I'll give you a very short introduction to graphene and what is the specialty about twisted bilayer graphene and the different quantum phenomena which are emerging from the strong correlation in twisted bilayer graphene. And then finally, I'll show you some of my result on magnetic field driven different phases. And finally, I'll show you that if you go at a very high magnetic field, which is 1 magnetic flux quanta of twisted bilayer graphene, then basically the flat band returns with strong correlation, and you will see again all these different correlated phenomena at high magnetic field. Well, to begin with, it all started in 2004 when Andrei Game and Konstantin Novoselov find out a very simple yet elegant way of getting a single atom thick layer of graphene from the bulk 3D graphite crystal. So it was a very simple trick. So they took a Scotch tape and placed a 3D bulk crystal on top of that and peel it multiple times until you get a very thin uniform layer of graphite, and then they place it on top of the silicon oxide substrate and finally peel off the full Scotch tape. And if you see under the optical microscope, there will be few regions where you will have a single atom thick layer of graphene. And this beautiful discovery gave them the Nobel Prize in 2011. But probably the happiest of all was this magic Scotch tape company who put immediately a name Magic on their this product. but but what follows next? So people immediately found out that there are multiple materials out there which can be exfoliated by the same trick by using this Scotch tape method. And people, excuse me, people found out that there are different semi-metal, semiconductor, insulator, topological insulator, even superconductor, which can be exfoliated by the same trick. And very soon they started putting one material on top of another, just like a Lego. It's called Lego in 2D materials, and observed completely different phenomena in this 2D heterostructure. Right, but so far people were only putting one material on top of each other just as it is. They didn't try to rotate them or twist them in between the layers. But what happens if you try to twist them? So we know if we have two periodic structure and we try to rotate them by a certain angle, then basically they will form a different periodic structure. Sometimes they have the same symmetry, sometimes you can break the symmetry, but they will form a different periodic structure. So here, for example, I have two layers of graphene which are rotating by a certain angle, and at some angle you will form the commensurate structure where you have the periodicity intact, and at some of the angle you will break the commensuration and you would not have the symmetric structure. Finally, here my two layers of graphene are rotated by 1.1 degree with respect to each other. And then you can see they still have the hexagonal symmetry, but with a higher periodicity. So now my lattice periodicity is much higher than the graphene periodicity, right? So this introduces a superlattice potential in my system, which can reconstruct the band structure of graphene. Okay. So just to give you a very brief introduction of graphene, so we all know that graphene is a honeycomb hexagonal lattice made of carbon atoms. So basically from chemical point of view, they are same, they all are carbon. But if you consider the crystallographic structure, there's pink ball and the light blue ball, they are different because of their interatomic interaction, right? So we call them A and B super sublattices, and they form the unit cell in my graphene crystal, right? So if we write down the Hamiltonian for this system, then they look exactly like the Dirac equation in 2 dimensions for massless particles. And if you solve this Hamiltonian, then you get this band structure in energy momentum space, where if you zoom in to one of these minima, where the conduction band and valence band touch each other, you will see that they have a very linear dispersive relation, right? And we call this Dirac cone. And in graphene, you can basically tune the Fermi level of your system by applying gate voltage that I'll explain again later. But what happens if you put one layer of graphene on top of another? So here, for example, I have two sheets of graphene shown by the blue and red color. So in reciprocal space, in momentum space, you have two Dirac cones which are almost close to each other, but separated by a distance given by k theta. Theta is your twist angle between two graphene layers. So in this picture, there are two energy scales which are very important. One is the kinetic energy of your electron given by the Fermi velocity at Dirac point, and another energy scale is the interaction between these two Dirac cones or these two graphene sheets in the real space, right? So at this point, I have my interaction energy almost close to zero and the maximum kinetic energy. But then if I try to twist them more, at a certain point, these two Dirac cone will have hybridization between each other, and the interaction energy will start to increase. So right now my interaction energy 2W is much lower than the kinetic energy, but it has a finite value now. But what happens if you rotate them exactly by 1.1 degree? Well, so at this particular angle, the interaction energy becomes significantly higher to the kinetic energy, or almost similar to the kinetic energy. And your band will hybridize in such a way that at lower energy scale, you will form almost a flat band. So flat band means your Fermi velocity of the electron close to the Dirac point will be almost zero. So if I see this in the reciprocal space, then you have two Brillouin zone coming out from two graphene sheets shown here by these red and blue hexagons. And if you have the superlattice potential on top of that, which means if you rotate them by this 1.1 degree, then you make these small black hexagons which are coming from the superlattice with bigger periodicity. So in the real space, if you have bigger periodicity, in reciprocal space, in momentum space, you will have the small Brillouin zone, okay? But still you have the hexagonal symmetry. And if you calculate the band structure for this particular twist angle 1.1 degree, then you'll see there is the very flat band at lower energy scale, which is shown here by black color. So the width of this band is of the order of 10 milli-electron volt, let's say. And on top of that, at higher energy scale, you will have some dispersive band, which is shown here by the red color. Well, so what does it mean to have a very flat band in your electronic band structure? So that means your electrons are almost localized there. Their velocity is almost zero, and since they are localized at a certain point, they have a very strong interaction between each other, right? So here I have shown you the density of states of the electron on top of twisted graphene sheets. So the black sheet is my twisted bilayer graphene by twisted by 1.1 degree, and there will be certain region in the real space where you will have one layer of graphene exactly superimposed on top of another layer, which is called AA region, but there will also be certain regions where you will have AB or BA type of arrangement. And if you see the density of state, at a certain point, you will have a very highly localized electrons, which are shown here by these peaks. And at certain region, you will have almost zero density of states. Okay. So so what happens if you have a very highly localized and strongly correlated electrons? Well, it can be understood a little bit by Harvard model. So in this Harvard model, in the Hamiltonian, you have again two dominating terms. One is the hopping energy from one side of your lattice to another side, which is given by small t here. And another energy scale, which is very important, is the on-site interaction energy. So how much energy will it cost to move one electron from one place to another, let's say. And the ratio between these two energy scale is very important, because in strongly correlated systems, sometimes you have your on-site interaction energy very, very high, and you have different insulating states, like Mott insulator or different correlated insulating state. So in this system, the ratio of U by T is a very important parameter to understand what is happening in this highly localized electronic system, right? So here I will switch the gear a little bit to show you how we actually fabricate these devices. Okay, so we have different.
Excuse
Yes.
me, sorry, I missed something. So in the previous slide, what is
Yes.
the U is in the, U is smaller than T, right? So it's in weak coupling limit, where you showed the Hubbard model.
Yes. So this is just to show you why U and T Hi.
Hello.
Hello.
Yeah. So
Yeah,
I can hear you now. Yes.
Sorry, do you have any other question?
Yeah. No, actually didn't get your point. I mean, something because of this unstable internet connection. Just could you repeat, please? What did you say?
Oh, okay. Sorry. So I said that in twisted bilayer graphene, if you twist them by close to this magic angle 1 degree, then U will be much higher than the T.
Oh, okay. So it's strong coupling limit. Okay.
Exactly.
Okay.
Yeah. So it also it also depends on other factor. For example, how what is the electrostatic environment of your system, let's say, but because that will also change the T factor. But so if your band is almost flat, like the close to this 1.1 degree, your U is much higher generally.
Okay. Thanks.
Thanks. Okay, so how do we make these devices? So basically, we make a heterostructure of twisted bilayer graphene covered with another insulating layer, which is hexagonal boron nitride. And all this process we do by using a PDMS PC which acts as effectively act as a glue. So you can think of, you have a very smooth surface which is your PDMS, and on top of that you put PC. This is a long chain polymer, but very adhesive to these 2D layers, either graphene or hexagonal boron nitride. So you put the PC on top of your PDMS, and then you approach that on very close to your 2D flake, either HBN or graphene, which is deposited on your silicon oxide substrate. So if you touch this combination of PDMS PC on your two-dimensional flake and detach them, the flake will come on your PDMS PC stage. Okay. So first we exfoliate these insulating layers, hexagonal boron nitride on silicon oxide substrate. Then we come up with this PDMS PC stack and pick it up around 110 degrees centigrade. So now you have PDMS PC and then top HBN, right? Then on another substrate, we prepare a single layer of graphene, and we cut the graphene, that graphene in two pieces by using an AFM tip. And then we come again with that top HBN and pick up the first layer of graphene, and then rotate the other layer of graphene, which is sitting on my substrate now, by exactly 1.1 degree. And then finally pick up the second layer of graphene. Then we have to cover the twisted graphene by another insulating layer, which is again an hexagonal boron nitride. And then finally we try to pick up a graphite layer, which will act as my gate. So I will tune the Fermi surface of my twisted bilayer graphene by using this metallic graphite layer, right? And then finally I deposit all of these layers, the 2D heterostructure, on another silicon oxide substrate. So after making the stack, we take them to the clean room for making the actual electrical contact to these stacks. Okay, so here is an optical image of my twisted bilayer graphene covered by hexagonal boron nitride, and in the middle I have this thin graphite layer, which will act as my gate later. So but before making the electrical contact, I want to have my device in a very specific geometry called Hallberg geometry to measure the 4 probe in all my quantum transport measurement. Okay, so I etched the full stack in this particular Hallberg geometry structure, and finally I deposited gold on each of these legs in order to have the electrical connection, where I will finally connect my instruments in the end, right? So, and this is the very simple 4 probe measurement scheme. So we bias the device by applying a current and measure the voltage in between these 2 legs. We can either measure the longitudinal resistance or the transfer resistance of the device. And in the end, we apply the gate voltage to tune the carrier density by using the graphite. So basically in the graphene, you have the Dirac cone, and generally if you don't apply any gate voltage, you are sitting exactly at the Dirac cone, right? And then as you start applying the gate voltage, basically you will tune the carrier density or the Fermi energy from the Dirac cone to the higher level, either in the conduction band or in the valence band, depending on the which polarity of gate voltage you are applying. Okay. So the theory of this, that you will
I
have
have
a
a
very
question here.
yeah.
Yeah. The thing that you were saying that by modulating the electric field, we can change the thing to conduction band or to the valence band. But here the thing is not of the graphene, rather something hybridized bands, right? I mean,
Exactly.
yeah,
So you have a flat band, so that is
yeah,
much flatter than the Dirac cone I'm
yeah,
showing here, but
yeah,
still
yeah.
you have a conduction band and a valence band, right? They are much flatter than the Dirac cone here, but still you have two bands in your around your zero energy level. So you can tune the Fermi energy within that flat bands.
Okay, and the density of states. I mean that by modulating, we achieve different in the different position of the density of state region, right? So,
Right.
but here you are saying your density of states is localized at some positions in the momentum space, right? So while
Right.
modulating, I mean the same kind of behavior is also expected.
Right.
I mean,
So yeah, that's a very
in
interesting
contrary
question.
to the graphene, yeah, contrary. I mean, in
So
contrary to graphene, the thing should move continuously. While in this case, something in some periodic nature, it should appear. I mean, as
right. So if you inside the graphene, if you tune the carrier density, you will see a very continuous change of your resistance or conductance, because you are tuning it more like linearly. However, in twisted bilayer graphene, you will you have a flat band, but due to the strong interaction, you will also have small gap opening. So you will see that if you tune the carrier density, you have some metallic regions and then some insulating regions, and within that flat band you will have these different um, like highly resistive states or low resistive state within the flat band, because you are basically tuning through different density of states.
okay. Thanks.
Right. So okay, so the theory behind this, that if you rotate two layers of graphene by a certain angle, at a very specific angle, you will have flat band close to 1.1 degree, that is we call first magic angle, or 0.5 degree that we call, let's say, second magic angle in the series. You will find flat band. So this theory was out there from 2011 and people were trying to make these devices, but the 1.1 degree rotation between these two graphene sheets is not a stable configuration. So most of the times when we try to make these devices, they relaxed back to the more stable configuration, which is away from 1.1 degree. And we end up not having properly twisted devices, right? So it took them many years to finally make a device which was twisted exactly by 1.1 degree. And this discovery was in 2018, when Pablo's group in MIT find out that if you rotate them exactly by 1.1 degree, you will see different correlated states in the system. For example, starting from correlated insulator to even superconductor. So just to explain the phase diagram here, all these color plots are longitudinal resistance as a function of temperature, and x-axis is my carrier density. So here I'm in the x-axis, I'm tuning the Fermi energy, right? Either in the electron side for the positive part, or in the hole side, in the valence band for the negative side, right? And the dark red regions correspond to very high resistance state, and dark blue regions correspond to very low or sometimes zero resistance state. So you see, you tune the carrier density and you are going through from different highly resistive state to sometimes even superconductor, right? Because all these measurements were done close to 35 millikelvin, so they could actually see the superconductor at this temperature. And the band insulator means you completely fill the first flat band, because if you remember the band structure, then you have the flat band, and on top of that you have the highly dispersive band, but there is a band gap, single particle band gap in between, right? So once you reach on top of the flat band, then you have a huge gap in your band structure, and there you have this highly resistive dark red region. So these were already
Can I ask a question? Sorry.
Yeah.
Can I ask a question? You said
Sure.
that in the initial attempts, people could not get that 1.1 degrees angle because the lattice reconstructed and went back to 0 degree perhaps. So what was the trick that was used to make it happen, that it stays at 1.1 degree?
So they right. So my guess is, for example, Pablo's group, they got this result in 2018, but they were trying it for at least 3 to 4 years, and so if you, so the stacking process that I showed, that you take a HBN and then you put one layer of graphene, and then you put another layer of graphene rotated by 1.1 degree, right? But
Right.
in the beginning, what they were doing, they were not cutting the graphene layers in half. Rather, they were putting their HBN on one part of the graphene, and if you just take it out, then you will cut the graphene where you are touching your HBN. Basically, HBN will peel off one part of the graphene and the other part will remain on your substrate. Then you rotate and then pick up the other part. But this probably used to cause a lot of strain, which might relax the twist angle in the end. So what they did in the end, that they first cut the graphene so that you can completely separate them out. So when you are picking up one layer of graphene, you are not basically rotating them. So you are not basically putting any strain on the other layer. So you pick up one layer cleanly and then you rotate the other layer and pick it up. So this might increase their the efficiency of getting these devices, but also I think in the end it is really probabilistic that if you make, I don't know, 10s or 12s of the 20 of devices, at some point it just sticks there. So we still don't know how to control it with 100% efficiency. We still make yeah.
Okay, I understand that it is with some probability that you will get the right twist angle. But the point is that I thought the reconstruction happens to minimize the energy, right? So where
Yeah.
does the strain come into the picture here?
So you have to think when the graphene is a very flexible layer, right? And if you have, so if you if you introduce any strain on that layer, and in the stable configuration, when you have all of your layers together, then they will try to relax back. So this lattice deconstruction will happen, but also if you have certain mechanical strain, that will try to relax in the end at the stable state. And that relaxation, so if you, let's say you already twisted them by 1.1 degree at certain part, but in the other part, you have kind of weird strain in the two layers, and that strain is trying to relax. So in mechanically, when they try to relax, they will probably again change your this 1.1 degree twisted. So you can think of like a very thin layer of I don't know, some film or some plastic, and if you have wrinkles or strain in one part and you try to like make them uniform, that strain will also affect your unstrained part, right? So it's like microscopically this can happen. So these are like mainly, the main problem is 1.1 degree is not very stable. And also like when we do this micro manipulation, we have like a stage, like a mechanical rotational stage, and then we do all these rotations, but right, but microscopically we don't have the full control on how they are actually touching each other, because the stacking process is sometimes a bit complicated, because you have different problems in different state, let's say, and strain or like uniformity of your hexagonal boron nitride, all these kind of play a role. Or if you have a, let's say, a huge air bubble inside your different layer, that might also change the twist angle or locally, right? Because that will give you a mechanical strain and it will change the twist angle locally.
I'm sorry if I'm taking too long, but the question is, okay. So if the question is, if in the ideal condition when everything is flat and there is no strain, and you put the layers together, won't they try to minimize their energy?
Yes, it will. But so the best part is once you touch them and they're nicely placed together, then since you have also two layers, two insulating layers on top of each other, basically you can think of they don't have anywhere to go. So they are stick to each other.
Okay, I see. So the HPN sort of holds the layers.
Exactly, HBN also yeah, HBN also kind of help to hold it there, let's say.
Okay, yeah, that is quite possible. Okay, so but it would not affect the actual interaction between the two layers, because if
It's an
HPN is kind of
insulator, right?
yeah, but it's sort of mechanically holding the layers, you know, in their position. So
Right. So once you form the superlattice, then everything is set, because then you have the superlattice potential, your band structure reconstruct, and you have a flat band.
okay, thank you very much. Please go on.
You're welcome. Thanks for asking the questions. Nice. So right. So they found the correlated insulator and superconductor, but not only that, on top of this state, people also found out that there are different magnetic state in the flat band, and also they found quantum anomalous Hall effect in the system. So all these different type of phenomena within a single flat band leave us with a very important question. So what is the different symmetry or topology of the ground state inside the flat band, right? So at zero magnetic field, you have the flat band. In the energy momentum diagram, this is within first Brillouin zone, you have the flat band, which is of the order of, let's say, 10 to 20 milli-electron volt. But due to the strong interaction, all these the flat band can split in 4 different mini bands. Okay, and the strong interaction can induce either, so in your system in twisted bilayer graphene, you have the C2T symmetry intact, which is inversion symmetry multiplied by the time reversal symmetry, right? So that is intact. But because of the interaction, you can break this symmetry and you will have different mini bands, different within the flat band, you will have different mini bands with different symmetry, let's say. So this is at non-zero magnetic field, and you have, so your Fermi energy lies within, and you have two sets of band above and two down, which are valence band and conduction band. But they have now different Chern number, let's say. So nu equals to 0 means charge neutrality point. So I didn't change my carrier density yet. I'm exactly at 0 carrier density at 0 energy level. And I have two orange bands which have, let's say, Chern number +2, and two blue bands which have Chern number -2, right? But then if I try to fill my band slowly, so nu equals to 1 means I filled my band by 1 electron per unit cell, okay? Then I tuned my Fermi energy a little bit, and I filled one blue band, which has now Chern number -1. So these two band has splitted again, and I have a total Chern number of +3. And same as nu equals to +2, which means I have 2 electrons per unit cell. And so if I consider all the bands filled below the Fermi energy, then I have 2 orange band, 1 blue band, which will give me total Chern number of +2. And finally, if we consider 3 electrons per unit cell, I'll have a total Chern number of +1. So this shows us so basically without a very strong interaction, you will think that you have one flat band, and if you just calculate the Chern number from the very phase, then you will have a single Chern number for this single band, right? But in reality, we see that as we keep on filling the flat band, the interaction basically breaks the band, split the band in different mini bands. Each of these bands have different Chern number, right? Which is not expected from the single particle band structure calculation. So in the experimental data, we observed that. So here, this is a color plot of longitudinal resistance as a function of magnetic field, and my x-axis is the carrier density, filling factor, right? So as I go away from the charge neutrality point, which is my filling factor 0, as I go in the positive side, at certain filling factor, I have different Chern insulators, which are shown by this almost 0 resistive state in blue color, right? So at a certain magnetic field, from each of the filling factor, I have different Chern insulators. So how do I make sure that they are Chern insulator? If I measure the Hall resistance at this particular magnetic field and carrier density, then for each of the Chern insulator, I have a very quantized Hall resistance at that particular carrier density. So this gives me a very special sequence of Chern number inside the flat band, which is from charge neutrality point, I have Chern number ±4. From the filling factor 1, I have Chern number ±3. From filling factor 2, I have +2, and filling factor 3 gives me +1. So this spatial sequence of the Chern insulator emerging from different filling factor of my flat band tells me that the interaction breaks the symmetry, inversion time reversal symmetry, and I have 4 different mini bands with different topology now. Okay. So on top of that,
sorry,
yes.
Can you go back to the previous slide?
Yeah.
So nu here is discrete numbers, right? but in the plot where you plotted sigma xx versus mu, it seems continuous. I mean, not seems, but it's continuous. So how you manage
Yes.
to get values in between, let's say, two discrete values of mu?
So nu is so you right. So when I'm saying it's 1 electron per unit cell, basically we in the real system we are dealing with 10 to the power 23 electrons, right? So you are putting more electrons in the band, which is of the order of 10 to the power 16 per meter squared, let's say. So, but if you normalize it by your unit cell of the system, then you can find it 1 electron per unit cell. But within that, you have 10 to the power 14 or 10 to the power 16 number of electrons. So you are changing that carrier density continuously by tuning the gate voltage as I shown earlier. But if you just normalize it by your unit cell and the device geometry, etc., then you can consider, okay, this is my 1 electron per unit cell. But in the reality, you don't have 1 unit cell. You have, I don't know, thousands of unit cells in the system.
Okay, got it. Thank you.
Right. So this was inside my flat band. But what happens if I go beyond the flat band? If I go to the higher dispersive band that I shown earlier with the red color, right? So we found that at higher energy, so this is my band structure again. I have the flat band, which is blue, and on top of that, I have dispersive band, which is shown here by red. But if you zoom in closely to top of the dispersive band, then you'll see that there are basically two dispersive bands crossing each other. And the crossing point, again, we call a Dirac point, because at that particular point, you have, again, a linear relationship. And if you apply magnetic field to this band structure, each of these band will split into different Landau levels, right? So basically, this is a magnetic field versus carrier density plot, and you apply magnetic field, you have different Landau levels with different Chern number, let's say. So you will have C, C+1 or C minus 1. But at certain magnetic field, so you have each of your band has been splitted in different discrete energy levels now, and you are tuning your Fermi level from top of the band to inside of the band, let's say, right? So at certain filling factor, you will have two Landau levels from two band crossing each other, right? And there you will have a Landau level crossing, and this will happen at a very certain magnetic field value, because if you change the magnetic field, you are also basically changing the gap of your Landau level, right? So this was experimentally observed. So here the carrier density is from +4 to +10 or -4 to -10, depending on electron or hole doping, which is away from the flat band. So inside the flat band, you have until 4 electrons per unit cell, but beyond that, you are tuning the carrier density more, right? So you were within the higher dispersive band. So here again, I have resistance as a function of magnetic field and carrier density, and all these dark blue straight lines are Landau levels. So if you zoom in close to lower magnetic field region, then you will see one Landau level is emerging from one point, and at a certain magnetic field, it stops, it kind of gets interrupted there. And then if you keep on increasing the magnetic field, it continues again, which means that you have two Landau levels coming out from two different bands are crossing each other. And at the crossing point, you have an interruption, you have a break in the Landau level, and then again it goes on as you keep on changing the field or the Fermi level, okay? So this we try to understand what if we can, from this experimental data, if we can somehow understand the exact band structure of for the higher energy dispersive band. So here we plotted the resistance again as a function of reverse magnetic field and Chern number. So for example, Chern number -16 gives me a Landau level with filling factor 16, okay? And then you see that these white dashed arrow, they continue, but at a point they get interrupted, and then at high magnetic field, they continues again, okay? They continue again. So in the right-hand side, I have a theoretical model where I calculated exactly at which magnetic field this interruption or this break of Landau level will happen. So then I compare my experimental data with the theory and find out that there is basically a perfect match between the experiment and theory. And from this, I can exactly calculate the band structure of twisted bilayer graphene in the system. Okay. So here I'll change a little bit. So this was all until 8 Tesla lower magnetic field. But what happens if you keep on increasing the magnetic field? So when we apply a magnetic field in our two-dimensional electronic gas, basically all of your electrons are rotating at a particular orbit called the cyclotron orbit. And if you keep on increasing the magnetic field, then this radius will be higher and higher. And at some point, your cyclotron orbit will match perfectly with your Brillouin zone of the lattice, right? And at this point, you have one flux quantum per Moire unit cell, and your band structure will reconstruct there. So you can think of at zero magnetic field, you will have the same band structure at that magnetic field where you have one flux quanta. For us, it was 30.5 Tesla for a twist angle 1.12 degree. So this is again a function of the twist angle of your superlattice. And for close to matching angle, the magnetic field you need to achieve one flux quantum will be close to 31 Tesla, okay? So in the band structure, we have seen the similar feature. So at zero magnetic field, again, you have a flat band, then you have dispersive band. And also if you go to this 30 Tesla at 2 pi magnetic flux quantum, then you will again have flat band, but probably the width of this band is different. And also the symmetry of the flat band at high magnetic field might be different, but qualitatively they will still have the strong correlation of the electron inside the flat band, okay? So people have observed this type of Hofstadter spectrum in different superlattices, mostly with graphene HBN superlattice, where they see that at phi naught, you have again the similar behavior starting there. So it's kind of fractal behavior. You have different Landau levels coming out from zero magnetic field, but once you reach phi naught, one magnetic flux quantum, everything sort of restarts there. So you have again the similar band structure there, okay? And also a couple of years back in our group, people observed for the similar behavior for small twist angle, which was 0.45 degree. But 0.45 degree doesn't really have such a flat band, which will have a strong correlation inside. So it was almost similar behavior what people have observed in graphene HBN superlattices. But in magic angle twisted bilayer graphene, you will expect to see some Hofstadter feature with very strong interaction, okay? So this is what we observed. At zero magnetic field, you have the blue curve where you have highly resistive peaks at different filling factor, which is my correlated insulator. and on top of that, you have a superconducting region. And if you go to 30 Tesla, again, you have highly resistive states, which are correlated insulator. So, which means that around that magnetic field, you have a flat band, you have the reentrance of the flat band again, which comes with strong correlation, and you have the hi.
मछली हुआ है क्या? पता नहीं, देख एक बार आप देख लीजिए क्या है कि नहीं। अच्छा अच्छा, ठीक है ठीक है।
Okay. Can I continue?
Yeah, I think some audio problem. Yeah, you can continue.
Okay. Right. So in the color plot on top, you have the resistance again as a function of magnetic field and carrier density. And we have magnetic field tuned from 0 Tesla to 30 Tesla. And you see that the dark red regions, which gives you the correlated insulator, you had them at lower magnetic field. And as you keep on increasing the magnetic field around 30 Tesla, you again get them back, which means that there is another flat band close to 30 Tesla, which gives you the strongly correlated electronic states again, right? So as a result, we have different correlated states at 30 Tesla at filling factor +2 and +3. But so if we closely look at the low field versus high field data, then so here my carrier density is restricted between 1 to 3, because at filling factor 2, I have a strongly correlated insulating state, and I have different Landau levels emerging from that. Okay, so if I just consider one of these Landau level, then I'll see they are perfectly quantized at a filling factor +2. So this was my low magnetic field data, but at high magnetic field, again, from this correlated insulator, I have again one Landau level, which has the filling factor +2, which means that in the system, still the different symmetry of my system is kind of similar as zero field. So at low field and high field, they're kind of similar, because I showed you earlier that at lower field, you have Chern insulator +2 from filling factor 2. Okay, and that kind of remains similar at high magnetic field as well. So here I kind of schematically drawn all the Landau levels emerging from different filling factor and different flux. So at 0 flux, I have a set of Landau level. And if you go to flux 1, I have another set of Landau level emerging from different filling factor of the band. So, if you consider that all these Landau levels are emerging from a new Fermi surface, that will give you that. So if you within a flat band, if you have different Landau levels coming out from different filling factor, meaning that you have a band gap and your Fermi surface reconstructs there and give you different set of Landau level, right? Which means again at 30 Tesla, you have strong interaction and your flat band is breaking into different mini bands, which will give you different Landau levels from different filling factor. Okay, so from this we could confirm that around 30 Tesla, you have a flat band with strong correlation, and that gives you different set of Landau level and correlated insulator. Okay. So we again went beyond the flat band to see the higher order dispersive band. So here I'm just showing you a 1-year diagram, because we calculated the Hofstadter picture of twisted bilayer graphene for higher band as well. So here you have the energy versus magnetic field, basically the flux, and you have different Landau levels coming out from different magnetic field, magnetic flux basically. And if you consider these red or blue lines and map them as a function of carrier density and flux, then you will have the one-year diagram. Basically, this tells you how a Landau level evolves as a function of magnetic field and carrier density, right? So in this slide, on the left-hand side, we calculated the Hofstadter peak Hofstadter for twisted bilayer graphene. So the different gray lines, thin lines, correspond to different Landau levels, and the colored lines corresponds to different Landau level gap from different magnetic field. Okay, and in the middle you have the experimental data, where you can, if you kind of try to match the theoretical levels with the experimental data, that has been that has been schematically laid out in figure C, where we are comparing the theory with the experiment, and all the gray lines, light gray lines, correspond to the theoretically calculated Landau levels. Okay, and the colored lines are the experimental Landau levels that we observed, and you can see most of them matches with each other. However, there are certain Landau levels which we observed experimentally were not present in the theoretical model. So this Hofstadter calculation, the theoretical calculation, was single particle calculation without considering the strong interaction between them. Okay, so the deviation from the theory in our experimental data confirms that in the system, in the real system, you have strong correlation, which gives you different Landau levels, which are not predicted by the theory. Okay, so with this, we could confirm that around phi naught, around 1 flux quanta per unit cell, you have different, you have again a reentrant of the flat band and with strong correlation within the particles, and that gives you again a different flat band system to study within the same twisted bilayer graphene system. Okay, so with this, I would like to thank my PhD supervisor, Professor Dmitri, and the postdocs who were closely related to the work, Xiaobo and Alexandre, and all my other group members, and our theory collaborators, Professor Andrei Barnevik and his students from Princeton, and all the high magnetic field measurements were done in LNCMI Grenoble, where basically the quantum Hall effect was discovered for the first time, and different. And I would also like to thank different funding options at ICFO, and thank you all for your attention today.
Thank you, Ipsita, for the nice talk and giving us this much time from your busy schedule. So,
Thank you.
You have
it's really nice.
5-10 minutes. We'll just have a quick question answer session, and then we'll
Sure.
stop. So, if in the audience anyone has any question, please you can unmute and ask. And yeah, in the meantime, I actually have 1 or 2 questions. So I have some doubts in the understanding that AA and AB region, we all know that they happen because of different stacking orders. So primarily all these single particle calculations, etc., are done for AA kind of region, right?
Yeah.
And in a real system, we will have all the things like AA, AB, and the thing is that for a particular twist angle, it may be that AA region fraction is much more than other region. I mean, from the twist angle in which your devices are made. So, like that, we should understand the physics, right? And so in reality, like some effects of AB will also show up in the Hofstadter like Venn diagram. So that is do you expect that AB region Hofstadter will be much different from AA regions Hofstadter, and it will also show up in experiments?
So my guess would be, I really don't know, because maybe the exact Hamiltonian calculation might be slightly different, but my guess is, so AB region will, you can think of it as normal bilayer
Yeah.
the parabolic
Yes.
dispersion, right? So that will give you probably another set of Landau levels, but that is kind of that will be kind of a linear shift in your full spectrum, let's say. So for example, in twisted trilayer graphene, you have like a bilayer like band
Yeah.
structure. On top of that, you have a like Dirac cone, right? So,
Yes.
but the Dirac cone generally doesn't affect much. So it's mostly like, so you have different Landau levels for two bands, and basically you can also probe the different energy states by using this Dirac cone, but that does not affect the flat band of your system too much. So it's kind of, I would expect in the energy scale, it would be probably linearly shifted in one way or other.
Okay. Okay. And in like anyone is doing like electric field role on this Hofstadter, like I am expecting that although like the band structure may not be tuned that much close to magic angle in twisted bilayer with electric field like perpendicular, but let's say if there is any out of plane polarization phases, like I think Pablo also studied with twisted HBN, there are polarization states. So if suppose let's say we have some perpendicular electric field in twisted bilayer, and due to the polarized presence, the one means there might be some effect like the two layers can be slightly like the coupling can be changed between the two layers. So
that is I mean we are not studying that right now, but it would be really interesting because, for example, we for other projects in the group, we were also trying to make some double gated devices with top and bottom graphite like on top and bottom, and we observed that actually that itself significantly changed the phase space of your magnetic field. So we could only measure like until 8 Tesla, but that itself changes the phase space. So
means you are saying that just at keeping like the electric field 0, that also changes the phase space.
Sometimes yes, because probably it also changes the electrical environment, electrostatic environment of your twisted bilayer graphene. So that also changes. And if you try to apply a finite displacement field, that sometimes gives us a shift in our superconductor or different Landau levels little bit. We didn't study it thoroughly, but from the first few measurements we could see there is a change. Yes,
I see. Okay, interesting. And this high field data that you have, so what is the temperature for all those data?
Yeah, it's so they try to maintain. So basically it's a huge magnet. It's not a superconducting magnet. So you have like many different cylinder of magnet. Basically it's huge, and then inside you have the dilution phase. For the freeze, they try to maintain a temperature of around 40 millikelvin, but when you go to 30 Tesla, you are producing like a huge amount of heat, and also on top of that there are mechanical vibration. So basically your your electronic temperature would be close to hundreds of millikelvin. I would not expect very high, because we could still see the correlated state, which has a temperature gap of 3, 4, 5 Kelvin, but much higher than the general base temperature of your dilution phase.
I see. Yeah, anyway, it's interesting to see that these high field labs, I don't know how they function, but it's like huge man force going into it, I guess.
Yeah, I mean, it's also kind of crazy how much energy you spend in. So if you are at 30 Tesla, you within a blink of eye, you basically spend, I don't know, 10 megawatt hour, let's say. Yeah.
And just like last kind of question. So this dimension of devices, what you typically have like length and width, because I'm guessing that farthest electrodes will not show this much clean data, right? You always take closest electrodes in the longitudinal.
Yeah, sure. So yeah, whenever we measure, it's not also just because of the high magnetic field data, but sometimes if you take the furthest Hallberg measurement, probably you have slight inhomogeneity in your twist angle,
Yes,
and
yes.
you might not see superconductor or insulator. So we try to measure closest possible.
Yeah,
And
and that
the
would be
typical
something like,
dimension of that region, the effective device channel that we measure is width would be around, let's say, 2 micron, 2 to 2.5 micron. Length is again close to 2, let's say.
okay, yeah. Okay, so that means your devices are homogeneous within 2 micrometer length scale,
Yeah.
right? Yeah.
Yeah, that we can. Well, I mean, sometimes we have really nice homogeneous device, and you see similar feature all throughout the
All
device
throughout
with
the
a length of, with a length of, I don't know, 8-9 micrometer. But
Yeah.
yeah.
Okay, I think if anyone else has some question, otherwise let's kind of give a virtual clap to Ipsita for the time in spite of
Thank
having
you. Thanks a lot for being here today.
a bad cough. So okay, yeah, people are giving claps. Okay, thank you, Ipsita once again. Then we will slowly close the session, and thanks to all the
Sure.
participants who joined in this morning or afternoon. Okay, thanks.